partner applications. They're reporting to us too, in addition to obviously the first-party developer, and we pay them a bounty between $1,000 and $3,000. And so over the last 18 months, we probably triaged hundreds of different security vulnerabilities, but they all kind of fall into 19 different vulnerability classes, which themselves we group into 6 different categories. And that's what we're going to talk about today. If I wanted to talk about all of the 19 different security vulnerability classes, I would need about 90 minutes at least, maybe 2 hours. So I picked 6 representative security vulnerabilities from the 6 different classes, and hopefully we're going to have more information about that published in the next 6 months or so. How do we help developers in addition to Google Play Security Rewards program, which is GPSRP for short? We also have something that's called ASI. ASI is the App Security Improvement Program. App Security Improvement Program scans all applications on Google Play for security bugs or for privacy problems. And then we give developers a chance, what does it mean to give them a chance? We really urge them, even sometimes under the threat of getting the application suspended if we don't fix that. And so over the lifetime of ASI, which is, I think, started in 2016, we helped more than 300,000 developers fix more than 1 million apps, which is, to my understanding, the largest scale vulnerability remediation program in the world, and we're quite proud of that. At one point, we decided for ASI, we need to find our own vulnerabilities. Wouldn't it be easier if we just asked for vulnerabilities coming from external security researchers? So we started GPSRP. We now get more ideas about vulnerabilities. The idea is GPSRP, we get a vulnerability, and then in ASI, we generalize that kind of vulnerability and scan all apps in Google Play for that vulnerability. And in 18 months of GPSRP, we paid out nearly $200,000 in bug bounties to security researchers. If you want to learn more about Android security vulnerabilities, I've got a couple of links for you. Obviously, there's a section on our own Android developer website. It's called App Security Best Practices. It's not just limited to that one link. If you check in the left navigation folder, there's like 10 sublinks to that. So definitely make sure to check those out. And there's also two third-party websites that I would like to highlight. The first one is the Common Weakness Enumeration website, which is ran by an organization called MITRE, and essentially they try to enumerate vulnerability classes. And on my slides, I'm going to make numerous references to the MITRE CWEs, as they're called, Common Weakness Enumerations. And so you can always, for each vulnerability class, you can actually just look them up and see a lengthier definition. You can see how to audit for that, what consequences that vulnerability has, and so on. The second one I want to highlight is the OWASP Mobile Security Project. Also a very nice organization that tries to help not just application developers for Android, but security engineers across different platforms to recognize and avoid and mitigate security vulnerabilities. So definitely check those out. So here comes the main part. We're going to dive right into these 6 categories of vulnerabilities that I'm bringing today. The first category is a very simple one. The vast majority of you are going to be very aware already that there is such a thing as an insecure network connection, and we want to avoid that. And how do we do that? For each of these 6 different categories of vulnerabilities, I have an overview slide that looks like this. And because I'm not able to actually talk about all the 19 vulnerabilities, the one that's in boldface, that's the one I'm going to talk about. And the others I just got for you for reference, and you want to take a photo of these slides and then just look up CWE 319, for example, which is the common weakness enumeration of the MITRE organization for that particular vulnerability. For each of these vulnerabilities, I give a brief description. I also mention the CWE number and the reward that we're paying out to security researchers if they find this kind of particular vulnerability in any of our partner applications. And so for use of insecure network protocols, that's as simple as, for example, using HTTP to connect to a random website or a random server. And that's a read, and that's distinguishes from the other two, which is more of a write, to where you send data to the server that is kind of problematic. This one is a simple read. You connect to like HTTP ://myserver.com. So what can happen in that case, right? What can happen in that case is that an attacker that has the ability to modify your network request can inject code which can lead to certain security problems. For example, if there's an ability to inject JavaScript code into that request when it's coming back, then maybe malicious JavaScript code is executed in the context of your application, or maybe they can inject HTML code and then they can modify your login page, or they can just put up some kind of misleading phishing page where some kind of credit card or user credentials are phished. So that's the lowest amount of money we pay out, $500. It doesn't get lower than that. We used to pay out $1,000 for that, but so many of the top applications turned out to have this kind of vulnerability that we said, we don't want to go bankrupt with our payouts. We're going to have to kind of lower that amount that we pay out. The second two that I'm not going to talk about in detail is data transmission. Obviously, I send PII, personally identifiable data, over the web, and that means someone can intercept it and steal it. The third one is a very particular variant of that, where it's just about authentication over insecure protocols, where the data that is being transmitted over the network is login credentials, for example. So let's dive into the first one, use of insecure networks. What I have for every single one of the 6 vulnerabilities I'm going to present here is I've got 3 slides for each. The first one is the example code. The second one is how do we audit for that kind of security vulnerability in our code. And the third example, or the third slide, is how do we do better to avoid that kind of security vulnerability. And we're starting off very slowly. Okay, very simple. We are creating an HTTP URL connection to HTTP ://google.com. I don't even know if that's still possible anymore. I think all of the Google properties have moved to HTTPS only. But that's how it usually is. And obviously, it doesn't always have to look as obvious as this. There's in an ideal world, right, you can easily find this vulnerability by looking for HTTP with a string search through your own application. But maybe sometimes it's not that simple. And so what do we do, right? How do we find this kind of problem in our application? Well, we don't want to play whack-a-mole. So you can search for HTTP in your application, but there's better ways to do it, right? Ideally, you're going to use some kind of technology to shut down any kind of accidental insecure network connections, and Android has a couple of things that actually help you there, especially with the HTTP side. And so, starting in Android P, there's something that's called a network security configuration that you can define for your application, and then if you have such a network security configuration for your app, you can say, hey, don't actually allow any kind of insecure HTTP requests. And then you get some kind of exception, I assume, if it still happens. And so that's good. That's much better than doing the next thing, which is how do we crap for app code that actually indicates that an insecure network protocol is being used, be it HTTP, FTP, SMTP, and so on, or maybe your own custom protocol, right? That where you set up your own servers and you use your own like socket classes in the Android code, and then send the data that is potentially worthy of securing in a way that is just not secure and can be intercepted. You also want to understand what are the common entry points into network code in general in Android, and which are the ones that you use in your application. So there's very obvious ones like the URL class, there's also the URI class, there's the web view class, and so on. And for all of those, if you're in a position where you need to do a security audit, you want to understand if that particular class is being used in an insecure way, with like either a very straight HTTP :// URL being passed to the URL class or the web view class or whatever, or maybe in a different way where you accept user input of some sort and then you assume it's a trusted connection, but maybe it's not a trusted connection. That's where it gets complicated. And that's why you don't want to play that whack-a-mole. You want to make sure you got a network security configuration in place. You want to have maybe pre-submit checks for your code check-in or for your continuous integration system that makes sure that you don't use the old class HTTP URL connection, but instead you use the new class, which is HTTPS URL connection. And that class actually throws an exception when you try to open an insecure HTTP connection. So that's very nice. And there's also an Android lint check for those of you who use Android lint that can tell you you're doing something wrong that's probably insecure. With like the lint check is called insecure base configuration. I assume it's enabled by default. A second class of vulnerabilities is cryptography and authentication. So we're moving away from insecure network protocols. We're moving into crypto a little bit. And there are three different kinds of very common security vulnerabilities that get reported to us. The first one is embedded third-party secrets. The second one is embedded cryptography secrets. And the third one is leaking OAuth tokens. The very first one is a very common problem. I've talked to several people today just about that, where you essentially use a third-party service, and that third-party service provides you with an API key or some kind of token that you're supposed to embed in your application. And then how do you protect your token from like malicious attackers that extract the token and try to abuse your systems in some way? The second one, embedded cryptography secrets. Many algorithms that you use for cryptography use things like keys or what's called initialization vectors or other kind of constants that are being fed into the algorithm. How do you protect those, right? If you want to read more about this, that would be like CWE 321, for example. The last one is leaking OAuth tokens. It turns out that OAuth is actually surprisingly complicated to implement securely. And so we get a bunch of vulnerabilities all around leakage of tokens that then allow essentially attackers to intercept the token, extract it, and log in with your account. The one I picked is embedded third-party secrets, which seems to be a very challenging thing on Android. In the easiest case, it can look as simple as like past Twitter utils initialized, and then you have a key and a secret that Twitter provides you when you sign up for the API. And it doesn't always look like this. Sometimes it's in the manifest file, you embed a certain key for like your analytics engine or so on. Sometimes you have a configuration file, but in the end, the shared commonality between all these things is the key that you want to protect is on the device and easily extractable, especially if you have a dedicated attacker looking at your application. I would say the bad news is that you can't really do a lot to protect these keys, and so you have to rethink the strategy of how do you deal with those. So if you're in a position where you want to audit your own application for a list of interesting keys or tokens that are embedded, or if you maybe want to join as a security researcher, you want to find your own security vulnerabilities and applications, maybe even submit those findings to the Google Play Security Rewards program. What you want to do is try to understand first which third-party libraries are embedded in the application you're looking at, be it your own application, be it someone else's application. And for most applications, it's fairly simple, right? You look at the package names and you kind of figure it out. Even if the application is obfuscated a little bit, it's usually not too hard. Try to enumerate libraries, essentially. And then, once you've done that a couple of times for a couple of applications, you start building an understanding of which of these libraries actually have a token that is interesting, that I can try to extract, right? And there's, Twitter maybe, or Amazon, or we have had Pinterest API, we've had the app that I just forgot. Let's move on. In a very simple way, you can also just grab for key, password, login, secret, and you're probably going to find stuff. So that's very simple. So let's assume you find this. How do you mitigate actually? As a software engineer, if you build your application, the very first thing you want to do is ask your API provider, your third party, whether a business relationship or free relationship of some sort. Read up the docs, right? Very often they tell you, and so there are some companies which provide really good documentation. For example, AWS, there's a lot of applications that use AWS secrets that are embedded in the app, even though AWS, the documentation says don't do that, because then someone can access your Amazon Web Services and essentially run up your quota, run up your bill by abusing your storage or whatever. So AWS has a very, very good best practices section that tells you how to protect your key. Many others don't have such good documentation. And so there's always an opportunity to reach out and ask, send an email or whatever to a third party and ask them, what should I do with my key? Is it actually a sensitive key? Do I have to protect it? Because very often maybe the answer is, no, you don't have to protect it. We're doing like abuse detection in the back end or whatever. You don't have to take care of anything. But some others will also tell you, oh yeah, here's how we do it better, and this is what you have to do, and so on. So don't assume by default that you have to embed the key in your app. If there is no way for a third-party provider to help you with that, what you can do is you can spin up your own server and proxy requests through your server. Ultimately, what you're trying to do is you're trying to prevent abuse, and as long as the same key is used for every user, it's going to be very hard to understand who is running up the quota, who is abusing my service. So maybe there's an opportunity for you to use user-centric keys for every single connection that you make to a third-party server. Maybe the API that is that you're working with actually provides you with a way to automatically derive per user keys for their main key. That would be very nice. If that's not a possibility, you can do it yourself, maybe, by setting up your own server, and your application only talks to your own server, and your server talks to the third party. And so your server can essentially be some kind of application level firewall in that sense to try to filter out malicious requests, abusive requests, and so on. And it's maybe easier because then in that situation you can have your server create keys that are specific to a certain user and not globally used by all users. In general, it is very hard to protect something on an Android device because you can easily copy APK files, you can easily extract information from APK files, you can easily decompile stuff, and so on. You can easily do a memory dump, you can easily do everything, because you have to consider that if I'm a dedicated attacker, I can go as far as compile my own AOSP, right? And I can essentially put the backdoors that I need for extracting the secrets from an application that I want to hack. I can put these backdoors into my custom AOSP code, compile that, flash it, and then run your app. And so client-side protection of secrets is extremely hard on Android. Not just on Android, on many operating systems. Okay, so let's move on to the next representative category, for which we actually get a lot of vulnerability reports. Private file access. Private file access, in the very simplest way, is about sharing data in a way in files that allows attackers or other applications on the phone to read that private data. And Android has done a lot in recent versions to make it much harder to make this mistake. I think at the very beginning, in early Android versions, you just write stuff on the SD card, and then every other app can extract that, or just set like the world readable flags on a file, and then every other application can access that, right? Android has been shutting that down more and more, and it's also not a particularly interesting kind of vulnerability. So the one I'm going to talk more a little bit about is private data override due to path traversal. And this one is very good. It shows up all the time. Shows up in every operating system, shows up on web servers, websites, happens all the time, and it's very interesting. It's essentially when you give the user to you give the user an option to provide a path or a file name, and then they inject special characters like ... to get out of the directory where you want to store the file or to want to read the file from. And instead of that, essentially you trick, or the attacker tricks the application to read or write data they were not supposed to have access to. The last one, private data override due to zip file traversal, is a specialized form of that. Not many people realize that, but it's an ancient kind of vulnerability that relies on the zip file format, where in the zip file you essentially have a mapping between file names and files, compressed files, right? And the way it works is that an attacker can also set these specialized path and file names inside the zip file, so they can say, oh, I want to extract to // private / secret whatever. And that's very, very dangerous actually. So every time you unzip a zip file, you have to make sure that all the files that are in the zip file actually go into the canonical directory that you want to extract to, because otherwise they can go anywhere where your application has access to write to. So let's take another look at what can go wrong if you do private data override due to path traversal. The core problem is that applications accept user input that is maybe being manipulated by an attacker, and they don't actually double check that the user input is valid. In that case, what does valid mean? It means we're building a file or path, a file name or path name, which points to a certain directory, but the attacker is able to manipulate that user-provided data to point to a different directory than what we thought. So for example, here we have an output stream, a file output stream. We're going to try to write a file, and we want to write that file into our public directory, whatever that is. Let's assume it's, doesn't really matter where it is. Let's assume it's inside my application folder. That's a directory I declared for public writing, meaning public, any kind of user data can be written there. Okay, and I have a download subfolder, and then I have a file name. And if the attacker can manipulate the file name, then they can do something like, oh, let's write it to public directory plus download plus .. private directory, and instead of being written to my public directory, they can now do write the data into my private directory, which was maybe not intended. It doesn't always look as nicely as this one. Path concatenation is definitely a major source of these problems, but it doesn't always look as nice as this one. So what do we do? You want to find any kind of path or file operation that has variable input that can be manipulated by an attacker or legitimately used by a normal user, right? And you always want to make sure to sanitize that. And I don't know if it's on the slides. Yeah, we do have it on the slides. Okay, so how do we remediate that? How do we remediate the problem? So ideally, you want to cut off users from providing their own path in as much as possible. I acknowledge that sometimes that's just not possible. So what you want to do is that every time you build a path that is based on user input, you're going to have to sanitize that path. And the way to do it is you build your path, and you, at the time of building, it's like, it's unsanitized, kind of like you have unsanitized SQL statements before you clear them to verified SQL statements to avoid SQL injection, for example, or how you basically, you take some untrusted input and you turn it into trusted input. And with a path, the way you do it is you compare after creating that path, is it in the canonical directory where I expect it to be? And the file class actually has a method that's like .get canonical path or something like that. And that's the one you want to check, because that's the one that cannot be manipulated. So build first, check the canonical path. If the canonical path is actually matching your expectations, then you're good. If not, you probably want to error out. Unprotected app parts is category number, I lost count, but I think it's 4. Unprotected app parts, they are extremely common that you believe that you're shielding a part of your application from attackers, from users, from other applications, but then something goes wrong. And that happens so much that I actually have 2 slides for examples. It's the only category where I have 6 different kinds of vulnerabilities. The first one is unprotected activity. Obviously, Android provides exported activities and private activities for your application, right? And you declare that, for example, in the manifest file. And very often over time, what is actually you believe is a protected activity isn't even protected anymore because someone made a patch that for some reason unprotected it. Now you say, oh, why is that so important? It is so important because the kinds of activities that you accidentally invoke are sometimes stuff like send payment activity or upload photo activity. And then when you have something like the activity accepts an argument like where should I upload a photo to, and the attacker controls that, and suddenly they can upload photos to their own server, and that's not very bad. And we see these kinds of vulnerabilities fairly regularly. Unprotected services, kind of like unprotected activities. Absolutely the same kind of vulnerability class, probably less impactful because the average application does not have that many services compared to activities. My favorite one of this slide is actually typos and custom permissions. That's a really fun one because some of you may know that you can declare your own custom permissions in your application. You should never use custom permissions probably because they're broken in very many different ways. But the one that really amuses me is you've seen an application of a top developer where they declare something like my custom permission dot read contacts, and then they at use time they misspelled read contacts, and so they actually tried to protect something with like that read contacts permission, but it was never protected because the declaration was misspelled. I'm going to have to follow up with the Android lint team on that because maybe there's an opportunity to highlight this kind of bug. The one I picked to go into a little bit more detail is intent redirection. Intent redirection is fairly curious. It's essentially one intent passing some input data and then forwarding it to another intent, and that goes wrong a lot. The last 2, implicit broadcasts, sending and receiving. So many of you may know that if you send a broadcast, it can be intercepted by all kinds of applications that are on the device, unless you set the broadcast target, right? And there was a bug even in the in-app payment SDK that Google provides, where they forgot to set the target of Google Play. So any kind of malicious application was able to intercept in-app payments and manipulate them for all the applications that used our sample code from the SDK, which was a lot of applications. And so that was one of the things that the ASI program fixed, where we told the Google GMS core team, I believe, the Google Play services team, hey, there's a bug that makes it interceptable when someone tries to do an in-app payment. First, they had to fix it in their docs, and then we had to tell everybody, hey, you copied the docs from us, but the docs were wrong, so you have to update your code. The same goes if you actually if you're on the receiving end of an implicit broadcast, because you may expect some data on your application, but everybody who is also on the device and registers a receiver for this kind of broadcast can manipulate the data, and there's ways to set a priority of who gets to process broadcasts first. So if a malicious application gets between the broadcast and your application, they can like manipulate, for example, say you're waiting for a Bitcoin wallet address to send money to, and then suddenly an attacker changes out the Bitcoin wallet address, then your application is in a bad shape because the money gets sent to somewhere where you can never recover it. So you always got to check that you make sure that the broadcast that you're receiving is coming from the application you expect, and the application that sends it hopefully sets you as the target recipient. So let's talk a little bit about intent redirection. In the easiest case, the way it looks like, you have an activity, you have like an on-handle intent method in your code that takes additional intent information from the data that is passed to the intent, right? So one intent passes the data that's coming in, extracts information about another intent to call, and maybe even the arguments for that. And that exposes essentially your whole application to an attacker, because it's a very common way to have a public activity that can receive these intents, and then the public activity doesn't check what is actually, where do I forward what is the next intent I call, where do I forward the information that is coming in. And so a lot of attackers use that kind of chain to make it into the private activities in a way that you had never expected before. So the attacker calls a public activity with manipulated data gets extracted, and then the private activity gets started with that manipulated data. And we see that a lot, and it makes it very complicated to reason for developers about which ones of my activities are actually public and which ones of my activities are actually private. And if you essentially provide a jump board like that, then attackers can most likely manipulate a lot of your application internals. So what we're going to do about it, ideally you never allow activities to be started with user-controlled or attacker-controlled data, right? Because once you do that, you always have to verify that that data is actually legit and not manipulated in a way that you don't expect. And so the first step is always to get rid of user data as much as possible. If you can't do that, then you're going to have to go down the route of verification again and sanitation, kind of like I had talked about during the files example with the unprotected write. Unprotected write. I don't have a recipe for you on how to verify that an indirect intent essentially is legitimate or not. It depends on the use cases of your application, and there's no standard way to do that. For the files, we had the get canonical file path, which is at least one standard way provided by the API, but there's no such thing for that intent redirect, because it really, really depends on your application. There's a couple of things that you can do. For example, you can check class name and package name of the target, right? And then you can say, okay, the package name is myself. That looks good. The class name is one of my own public activities. That probably looks good too, because if you forward to a public activity, then there's nothing to be gained probably from that indirect jump from public to public, because the attacker could just call the public activity in the first place. Probably legit. So you have to decide on your own where do you allow this jump to, where do you not allow this jump to. You can also check for certain flags in intents. Flag grant read URI permission, flag grant write URI permission. I probably want to read the docs on that, because I'm not very familiar with those. Okay, so we got another category for vulnerabilities that don't quite fit into any of those targets. And these are just random things that crop up, and they're really funny sometimes, and sometimes really sad. The first one is incorrect URL verification. A lot of applications use URLs to determine if a domain they receive data from or sent to is trusted. And due to an unfortunate combination in how difficult URLs are in the first place, how the Android URL implementation had a couple of bugs, and other factors around that, it is extremely hard to verify that a URL is actually pointing to where you believe it points. That's the one I picked because it's so common, and we're going to talk about it a little bit more. There's cross-app scripting, which is also a very interesting security vulnerability that we see a lot. So there's a lot of applications that load untrusted URLs from other applications into their web views, meaning, for example, you get a URL to your application that is sent over, be it a broadcast or an activity start or whatever, and then you just load it, right? And if you don't properly sanitize that, you load potentially malicious JavaScript code, sorry. You you load potentially malicious JavaScript code into the context of your application. And depending on what you expose in your web view, an attacker can essentially manipulate internals of your application, or they can steal data that is also exposed to your web view. And that's an extremely common one, probably the most common one that we're getting these days as reports. A really amusing one was that we got only once, incorrect sandboxing of scripting language. So if you use an interpreter of some sort, like, oh, I want to embed like a Python interpreter into my application, you got to make sure that you're actually correctly sandboxing that one. That interpreter doesn't really have all the privileges that your application provides through the Android permission system. And I'll give you a very interesting anecdote about that one report that we received about that. That was a social network application that's very popular, not Facebook, just to avoid all speculation here, but it was a fairly popular mid-tier social network. And in that social network, you can have like your avatar, profile picture, whatever. And that profile picture had a very interesting file format that had like a little interpreter embedded in it. This was part of the image file format. And so an attacker was able to create a specially crafted image avatar, upload it to that social network's avatar library for other people to use. People would download it, use it as their own, and then the malicious code would essentially be run as part of that victim's user profile, and then could access the data from the user profile. So it's really crazy, right, how you have an image format that allows for arbitrary code execution, essentially. That's also why it's the highest reward, incorrect sandboxing of scripting language. If you manage to achieve remote code execution in a security-sensitive way in an application, we pay out $5,000 at this point for that. That's the highest one we have. It's about remote code execution, not about incorrect sandboxing of a scripting language. But incorrect sandboxing of a scripting language can lead to remote code execution. The last one, obviously, unprotected data on server. If you use your own standard database, we see a lot of like AWS databases exposed. You hear about security breaches of that kind all the time in the press. Just have some server, some database, don't secure it, and then someone realizes, oh, if I just change the URL to someone else's user ID, I get all their data, and so on. All right, so what is it with incorrect URL verification? I brought an example here, just one of the many ways to get URL verification wrong. There's a URI object, you use getHost, you use endwith, mywebsite.com, and because you use ends with, someone could just register mywebsite.com, and then the ends with check would still work on the string, and then you would load essentially what's coming from website.com instead of your own trusted website. The unfortunate part that I already described is it is extremely tricky to audit for this kind of usage. And I'm going to give you a second to take a photo, but now I'm scrolling over to the next slide. Because on HackerOne.com, there's a very nice article that is called Golden Techniques to Bypass Host Validations in Android Apps. And that essentially gives you all the information you need on how you can screw up host verification in Android applications. And I've seen the internal Google class, Java class, that tries to do host validation in a way that works around all these bugs and all these wrong assumptions, and it's like 200 lines of code or so. I only learned about the class recently, so I'm going to try to see if we can get that open sourced. In general, someone should write a library that does URL host validation, because if you don't have a vetted library, there's no way to do it right. So how do we audit in our own applications for that kind of stuff? Well, obviously you want to see every time there's a URL used, and it doesn't have to be a URL that you can grab for with HTTP, right? It can be a URL that is read from somewhere, some user input, some file, whatever. So look for these kinds of classes, figure out which ones of those are actually user-controlled, because user-controlled always means attacker-controlled, and then narrow it down to those attacker-controlled URL classes or UI classes. that are essentially used in an if statement of some sort, and then start auditing them. And then ideally, if you've written your library for hostname verification, you can just drop in your library at this point and say, hey, is this my own hostname, yes or no? And that's it already. I got through the vulnerabilities. And thank you very much, everybody. Really appreciate you joining me today. And I'm wondering if there's any questions.